Hello, everyone. Can you guys hear me? Okay, cool. Okay, we can probably get started. Okay, so yeah, let's continue our talk. So let's recap a little bit of what we talked about last week, because I think this week and the last week, and also maybe next week, they are, the topic are all some sort of like related. Okay, so um, essentially, is we talking about the 2-pointer, right? Right. So I think the first typical problem we talk about essentially is the you have a one array, you have a 2-pointer, then you're moving this one in a reverse direction, right? So something like this one, then you right. So this is one of them. Then this can be called start, or sometimes called left. This is called like endpoint or called right. Right. So the key idea, the key takeaway from this one is typically this problem will be examining all the possible, basically is all the possible IJ pair. So then in this case, if you examine all the IJ pair, then it's an algorithm. But we do the search space pawning by the 2-pointer. So we reduce the search space. Right? So this just gonna, so instead of examining O n square, like n square, like, basically is like n square, like, possible pair. We only need to examine like n pair, because every time we're moving, this pointer by one, then when those two reach, then normally that's where the algorithm ends, right? So this is essentially the idea about, how, we can improve the algorithm, right? So, for example, the problem we showed is like two sum and the most the container contain the most water, right? So then we starting to talk about the second one. Essentially, is a one array. Then you have a 2-pointer. Then moving the same direction, right? So this sometimes is also called a sliding window, right? So we're gonna continue to talk about this one. Essentially, is you have a, right. So if in case if this size is fixed, actually it doesn't really require this size to be fixed, because but it's just like in most sliding window problem, it's the size of the window is kind of like fixed. Okay, so then for this particular problem, really like we try to looking this one in a very generic, like, the scope. So basically, couple of things happening in here, right? One is uh, uh, for example, if this one the size is k, then suppose this is the index of I, then, well, I need to be a little bit more precise on this one. So yeah, so if this is index I, then this will be index I plus k minus 1, right? Then particularly this will be index I plus k, right? Right? So essentially is if this is array A, then essentially is when sliding happen, two things happening, right? One is you add, you know, this A plus K. Second one is you remove AI, right? So this is basically these two things happen, right? And at the same time, you are keeping certain, characteristic on this sub collection, right? You are like, there are certain, certain like, the kind of like the on this sub collection. What could be the possible that you're interested in? For example, you could be interested in the, for example, like sum, right? Sum is easy. Sum, or maybe product, you know, or maybe maximum, minimum, median, etc. Right? So basically, you're interested in some certain, characteristic on this collection of data, but this collection is a sub collection of the whole thing, right? So these are some kind of things when we analysis this type of problem, we have to keep in mind. Essentially, this also like for example, the example we are given is on the max, right? We are working on the the sliding window max, right? So but we can so we're gonna, I think in the sliding window max we talk about 3 or maybe 4 different methods, and there are so basically is okay, and we're gonna continue talking about that one, and because we still haven't reached the best algorithm. After we talk about that, then we can also looking at some other, some other things. I guess okay. So if you know how to do max, the minimum is really the same, right? The minimum is really the same, right? The only, but the sum product, basically some product is similar. Max minimum is similar. Median maybe slightly different. There may be also some other things, right? So so we will talk about that after we talk about the sliding window max. Okay. Right. So we say the first one is the brute force method. Basically, it's just examine. We're gonna we basically just gonna because every time we slide, we're gonna examine all k elements, right? So the exact reason, this algorithm has this time complexity of k multiplied by n. It kind of like you think about, the number of slides is roughly equal to n. Then every time you slide, you're gonna examine all the elements in the sliding window, right? So then we had this like basically is a modified one, right? Basically, say only examine k element when it's necessary. Right. So This one, clearly, this one will improve the average running time because you don't, compare with the first one, you every time you start, you're gonna re-examine everything. But in the second one, we basically say we illustrate there's also two conditions. When those two conditions happen, you don't need to examine the thing because you know exactly where the max is. For example, one is the new coming one is larger than the current max, right? The new coming one is larger than current max, then this will be the new max, right? This is number one. The second one is you basically know like the current max are still in this scope, right? So in both cases, you don't need to re-examine, the whole k element, right? However, this will not. So basically, this will improve on the average case, but not, but still the same on the worst case. The worst case essentially is if everything is in a reverse order, right? Everything is in a reverse order, then like so you still using this algorithm, you still like gonna examine everything. So that's, I mean, from time complexity perspective, the worst case time complexity is still the same. Okay, so yeah, okay, so then we then we're looking then in both of this one of the issue is essentially is when the max is out of the scope, you have to re you have to research, right? Well, or let me just say you have to rescan to find the max. In some sense, this basically means this essentially say, okay, I have this sub collection because for both method one and method two, I'm only keeping the current max. Basically, that's the only information I'm keeping for this collection. Basically, is this information is not enough, right? This information is not enough. Okay, essentially, in some sense, basically, we're saying not enough information. That's just the reason when this, if this max is out, then you basically is you kind of like think about it, you basically have a blank, right? That's the reason you have to rescan to get the next max, right? Okay, so then the third one we basically say we just say we keep the full order. Right? Keep the full order. So we basically say, okay, if there's no duplicates, if no duplicates in C++, we can using set. In Java, we can using tree set, right? And if we do have a duplicate in C++, we can using multiset. In Java, we can using tree map to work around with that problem. Okay, so then in here basically is adding and removing element is because in here for all this data structure, adding and deleting, is causing is like can I write in here? Oh yeah, I can. Yeah, okay. Adding and deleting is kind of like log k. Okay, then so that's reason this whole algorithm runs as n log k, because essentially is you have n sliding window. Every time you need to handle adding the new element, deleting the old element. Then to getting the maximum element, it's just because you keep the full order, the last element will be the maximum element, right? So I mean, this is kind of okay. I mean, so this is first n log k is better than nk because log k is smaller than k, right? So but the issue for here is a full like a full ordering is a much stronger condition than the maximum. Full ordering is a much stronger condition than the maximum. That's the reason you pay the cost. You pay some extra cost for keeping this actual information, right? So basically, it was extra cost paid for the ordering, right? So so this is exactly say when you analysis the the algorithm, you have to think about okay, what are the really the proper information you want? Essentially, is you don't want like too much. Also, you don't want too little. Okay, so that's kind of like the idea, right? One. So okay, so another one which is similar like this one is we're using the heap, right? Well, heap is also called a priority queue. Queue, right? So for this one will automatically keep the maximum element. Then, but because it's keep like kind of like keep the but still like adding and deleting is also like log k. That's the reason this one is still this one will this still runs like n log k. So this we will talk a little bit about heap and priority queue today. Okay, so I mean basically this one is kind of like from time complexity perspective, it runs almost the same as the previous one, right? And also we see last time this does not this still not gonna passing all the test cases because in the lead code there's the last couple of test cases has a very tight time complexity. It basically means this one still not run fast enough. Okay, so now this will introduce you for today. We're gonna reach the basically our final the best approaching for this particular problem. Okay, okay, yeah. All right. In order for us to understand this one, let's look at the one concrete example. Okay, suppose this is the sliding window. Okay, I'm just suppose I'm writing out this number in here, something like Okay, so far so good, right? So suppose this is the one in the sliding window. Okay. Oh no, I should do this one. Okay. So first, number one is what do we know is this current max is what? So this is pretty okay. We're gonna keep 7 for sure, right? The question is, besides 7, what else what else is we must keep? What else is so? What are the something that is no need to keep? What are something that we have to keep? Okay, so this is something we have to think about. Okay, let's try to think about this one. Let's first think about this one. So Do we need to keep this 4 and 3? Anyone? What do you think? What is your first intuition? Do we need to keep this 4 and 3? Anyone want to, nobody? You don't know? Okay. So our claim is this 4 and 3, because we have 7 immediate after that one, that means we have no need to keep 4 and 3. Because our sliding window is rounding from this direction, right? So 4 and 3 is kind of like the history, because there was already there was a larger number after 4 and 3, which means if this window contains 7, then you don't need to keep 4 and 3. That's essentially is this idea. Okay, that's essentially this idea. So this might need us a little bit of time to thinking through and understand. But this is the key to understand this. Essentially is in the current scope, once the 7 entered, 4 and 3 has no use. That's the idea. So using this sort of idea, you will then let's looking at this 3 number, then you will find out, okay, I do not need to keep 2, but I do need to keep 5 and 3. Okay, I think in order to keep 5, 5 probably folks can easy to understand, because when you're sliding over that, if all the numbers are smaller than for example 5, then when 7 is out of the scope, 5 will be the next largest element, right? 5 will be the next largest element, which means you have to keep 5. Similarly for 3, although currently 3 is less than 5, but doesn't matter because 3 come after 5. 3 come after 5. Okay, so basically so the claim is if you have suppose in this basically the inside can go like this. What we found out is this. Okay, so suppose we say we have a. Okay, so suppose if AI is less than AJ and I is less than J, basically means AI is less than AJ and AI is before AJ, then in this case, no need to keep AI. Okay, no need to keep AI. However, if AI is less than AJ, but I is greater than J, basically means AI is after AJ, then you have to keep, then you don't know, you kind of like, you have to keep it. Just like this case essentially is, 7 and 5. 7 is larger than 5, but 7 comes before 5. So when you sliding this one, 7 will be out of the scope, in which case 5 will still be in, 5 will still in there. Okay? So kind of like this intuition is kind of like say, okay, under the current scope, because AI will coming before AJ, coming out of the scope before AJ. That's actually the reason. As long as AJ is in the scope, I will never need to consider, I will never need AI. Just think about this 4 and 3, right? As long as 7 is in the current scope, as long as 7 is in the current scope, right? So you will never need the 4 and 3. Okay. So this is so by doing this one, what does that mean? Is eventually we can reduce this one to 7, 5, 3. Okay. And also, if we look at this one, they will forming some ordering. Okay, they were following some ordering. Essentially, is in this particular case, because we are looking at the maximum, So they are following kind of like a non-increasing order. But you can think about it, you can do the same thing for the minimum. Essentially, if you do minimum, then I think the one you're gonna keep will be something like some something like 2 and 3, I believe, because in which case, uh, right? So basically that's reason this is also called monotonic queue or stack, because this one is automatically monotonic, right? Okay. So we will see. We will have a. I think we will have a. We will have like a lecture just dedicated talk about this one. But right now, okay. So this part is very important. Okay. So then in terms of the actual implementation, how we can just reduce this one into this. So again, remember during the sliding window, we only need to worry about the two things. One is when we deleting the element. Normally, removing the element, removing the old element is relatively easy because like so that's reason in this case, the one thing we really need to care is when we're adding a new element. So let me just illustrate how we actually do this one for this particular one. So this is a 4, 3. So um, so just imagine you need, so this is 4, 3, 7, 2, 5, 3, right? So this is how we add in the element, right? So initially you only have 4, right? Right. So you got 4, you added into here. Now you're adding 3. So the idea is every time when you're adding an element, you you're going from the back. You're going from the back. If you see this element, if you see the element at the end of this queue is smaller than you can just remove it. So you keep removing the element which is smaller than you until you reach the first element which is larger than you. Okay. So when you're adding 3, okay, 3 is less than, so you will be looking like this until if the whole thing is empty. Now you get a 7 in here. 7, okay, you say, okay, 3, okay, 3 is less than 7. Okay, let's just remove 3. Now you reach 4. Okay, 4, okay, 4 is also less than 7. So of this one, you're just gonna keep as 7. Okay, now you get a 2. 2, okay, 2 you have no choice because 7 is larger than 2, right? Now you get a 5. 5 is okay, 2 is less than 5. So I can remove 2, but 7 is larger than 5. So you will keep this one. Okay, finally we got a 3. 3, yeah, well, you have no choices. So, right. So this is essentially is this. Okay. So this is how we like, keep, this element in the monotonic queue. And inside of the implementation, I will show the code very soon. But in the implementation, we don't actually store the actual value into the queue. We store the index of that element. So this is easier for us to detect when do we need to remove the element. Okay. So let me. Okay, so let's see this one. So, okay. I'm going to show the code a little bit. So the code itself is pretty simple. So again, so the line 6 to 16 essentially is this is just handling the the edge cases, right? For example, if the window is larger than the one, or if window size is 0 or window size is 1, right? So in here, uh, uh, we're using one of this data structure called DQ, right? DQ essentially is a double linked list. Okay, DQ is available in both C++ and Java. So okay, I'll actually explain a little bit about the DQ. So the reason we need to using DQ is because from the algorithm we basically say you are adding the element from the at the back, right? You also need to be able to remove the element from both front and the back. That's the reason we choose the data structure of DQ. Okay, DQ essentially is because for normal queue, you always adding the element at the back, removing the element at the front, right? But you can't you cannot like deleting the element uh at the back. But for the DQ, it's kind of like a double-ended queue because it's using like a double link list. Okay, so that's the reason it's very easy to remove the element at it's very easy to adding the element and remove the element at both ends. It's very fast. It's like constant time to remove it. So it's that's the reason we're using DQ. So so we initialize this DQ, then if we know the n, we know the k, then we know how many results we need. So we're just using that one. So this n minus k plus 1 is the number of the result we need. So we use another one to initialize, the result, right? Then we go through this array. We go through this array. So this is basically to to check whether because as I said, the one we push into the DQ is the index. Okay, so in here, the index I is actually point to the basically is the new element that will be added into the sliding window. Essentially, if you think about it at the end of the sliding window, this one will be one after that. Okay, so I will draw a graph, to explain this one very soon. So basically, this basically say, okay, basically this one is say, okay, well, and also because the way how we keep in the queue, that's actually the reason. If we want to get the maximum element, that's always the first element in the monotonic queue in this particular case, right? So then in here we just check whether this index is the one we want. Essentially, this is when the window sliding. We are saying, oh, is this the old element we need to remove? If that's the case, let's remove it. So remove first essentially is remove the first element. Then this is the one like before we adding this element, we need to remove. We're checking from back. We're checking from back. Then we see whether there was any element which is less than the current the one I want to add. But remember, 7 2, then you're adding 5. You need to remove 2, right? So essentially, I'm comparing the one at the last with the one I'm trying to add. Okay, if this one is smaller and also DQ is not empty, I will remove. I will remove it. After I remove it, either Q is empty or Q element in the Q is larger than the one I try to add. Right? In which case I'm just adding at the back. Because the new element we always adding, the new element will always be added into the queue. Okay, so this is just a thing. Then this is okay, when this is essentially say when should I starting to recording the result, because I could rewrite this one into 2 separate loop. Essentially say, okay, the first k element I'm handling separately, but I'm just say, okay, I don't have to do that. I just say, okay, this is when I is larger than k minus 1, then I know, okay, I'm already have k element. So that's the time where I should recording the results. Okay, So that's roughly is this one. So any question about this? I mean, it should still be relatively, straightforward. So let me just draw this one to help you guys to understand this one. Essentially, still goes like this, right? So this is your sliding window. This is the new element. So that's the index. This is the index I. Then I know this is the old element. Then this will be at the index I minus k. This will be the index I minus k. Okay. So assuming, assuming there's k, right? So this is, the reason. Then about the DQ, so essentially it's something like this. I think you have it's a double linked list. Okay. So every node will have 2 pointers, 1 point to the next element, 1 point to the previous element. So for example, this one will point to this one. At the same time, for the data structure itself, it has a 2 pointer, 1 point to the first element, the other 1 point to the last element. Now you know why removing first and removing last is very easy, because if you're removing the last, you always know where is the last element, and by the okay, I guess this is point to now, this point to now. Okay, so because you have a pointer point to the last element, then if you want to remove it, it's very easy. You just because you have a pointer point to the previous one, so you can just go from here. Then you just then you just repoint the last to the essentially the last dot previous, right? So it will go here, right? So for example, when remove, suppose if I try to remove this guy, what's going to happen is I'm just going to point to this guy, but I can go from here to here, right? I can go from here to here. Similarly, for the removing the from, it's also very easy, because if you're removing the from, then you kind of like just let this guy point to here, but you can go from here to here, right? So you know exactly where. So that's the reason. So this is kind of like the link I mean, I assuming you know a little bit about the linked list. I mean, like if you don't, I can send some actual. But if the folks wait in the summer this time, like basically refresh the memory, essentially say, okay, the linked list, right? What is good about the linked list? It's very easy to adding and remove an element. If it's a single one, then that's like yeah. But yeah, so this is essentially for this. Okay, so let's show the code again. Right, so basically it's so I think the one we really need is just removing first and removing last. Okay, then let's talk a little bit about the time complexity for this one. First is this is a linear algorithm. This is a linear algorithm. So we have a single loop looping through all the elements, right? So it's relatively easy to understand. Say 23 to 25. This one only run once, right? So this and the 32 is also only run once. I mean, for each iteration, it's only run once. So that's what I mean, right? So then 34 to 36 is for each iteration is also only run once, right? The only confusing part is this part, 27 to 30, because it looks like a while loop inside of a for loop, right? So, then you say, okay, how do I analyze this algorithm? How do I analyze this one? Because this one, sometimes it's only run once. Sometimes it will run multiple times, right? Because if you have remember, the example we are given, the queue initially have a 4 and a 3. Now you adding 7. You will basically remove 3 and remove 4, right? So there will be cases run multiple times, right? So if you just look at this one at one single iteration, that seems to be the case, right? But if you think about this one in a global view, right? In a global view, first is array has n element. Array has n element. Okay. The key insight is every element will be adding into the queue exactly once, because as a new element, you will be adding into the queue. And also, when it also will be removed from the queue exactly once. But when it removed, it's either at the beginning or at the end, right? Because that's the only time we can remove. Because, right? And we just showed, because it's a double linked list, the removing operation is constant time. That's actually the reason essentially say, if you look at this one at a global view, then every element will only be adding once and deleting once. That's actually the reason we never performing, repeatedly on any element. So that's actually the reason if you aggregate everything together, it's still a linear algorithm. So this is really a beauty about this called monotonic queue, or called monotonic stack. Okay, so that's actually the reason this is much so. Oh, I don't have this. So right. By the way, in the morning's class, some folks does not really know what is this big O notation. So I did spend a little bit of time to explain that. So I'm just curious how many people in here doesn't know this big O notation, because I realized I did not really explicitly talk about this one. So I could spend a little bit of time to talk about this one, but just checking, for the folks, you know, like, so essentially is this is the one we basically measuring the time complexity. So generally speaking, time complexity essentially is we think your running time is a function of input. Okay, that depends on your input, right? So your input could be, say, an array. Then we say that's basically the size. For example, like an element, right? Right. If you have a string, that's kind of like the length, right? For example, n character, right? Right. So you may also have, for example, 2D array. Then that's kind of like the number of the row and the number of the column, right? So this could be, say, mn, right? Or you have like the graph. graph will say, maybe the number of the vertex and the number of the edges, right? So essentially is in our particular case, for example, we're saying t is kind of like some function of n, okay, some function of the input side, the input side, right? And the time complexity is really just measuring for the asymptotic behavior. So we're trying to analyze the asymptotic behavior of the function. Essentially, we're only concerned when n is very, very large, right? We only concern n is very, very large. So in short, we need to remember two rules. One is constant scalar does not matter, okay? So for example, say you have two functions, say fn is equal to say 3n squared, gn is equal to 0.01 n squared. In this case, you have this constant scalar, okay, maybe let me just give it, say something like this one. This one says 3,000, 3,000 n squared, right? So essentially is we're gonna say fn is kind of like similar to the gn or to this O n squared. So when we talk about this one, we don't actually care about the this constant scalar, okay? Because essentially is we're looking at the overall magnitude, because when n is large enough, this thing will be just gonna it's gonna reach the same magnitude, okay? So this is rule number one. Rule number two is we should ignore all the lower order terms. Especially okay, I guess I spelled this one wrong, sorry. So especially if your time complexity is belong to the polynomial family, then then we basically know like the degree of the polynomial kind of like determine you are looking at the highest degree, right? So the lower degree will that's what we call the lower term. Okay, that's what we call the lower term. So for example, maybe your function is something like 0.01 n to the cube plus 3,000 n squared, plus this one n plus this, right? So you have four terms. You don't firstly again you don't care about the scalar, the coefficient in front of it. Or what you really care is the ordering. Okay, so essentially is the well the in this case the degree, right? N cube is the largest one in degrees. That's actually the reason when n is large enough, all the other three ones they are all what we call the lower order term. Essentially say when n is large enough, we are looking at the function growth, then n cube will be larger than all of this, right? N cube will be larger than all of this, right? So in this case, right? In this case, that's so we don't. This is what we call the lower order term. Okay, these are the lower order term. So then the common like time common time complexity, the one the most common one is the polynomial one. Polynomial one. So this one is a polynomial, right? So in here, it's kind of like easy, you know, we're saying, you know, O n to the A will be larger than O n to the B if A is larger than B, right? Yeah, I think in most cases this one is greater than 0 because, you know, yeah. Second one is the log, right? Log one basically is, you will basically say kind of like, you know, n to the A will always larger than log n, you know, as long as if A is larger than 0. So, you know, I don't think you have anything like the exponential part will be negative when we're talking about the time because I don't see any algorithm is like running time is like, for example, 1 over n. I don't think that that's the case. Okay. But A normally is like, you know, integer, but positive integer, but A can also be something like square roots or cubic roots or those kind of stuff. Okay. So this is something you need to be aware of. But this still stands. Okay. This still stands. Then since we talk about time complexity, let's just bring actual 2 or 3 minutes also talk about the space complexity. Space complexity is essentially similar, right? Space complexity, the only difference is we are looking at the actual memory space is needed, and we also want to model this one as a function, think as a function of input size. One of the key words here is actual, because you got to read the input, right? If you don't read the input, then you can't really do anything. But what's happening here? Okay, but this space complexity basically say, besides the input, do you need some actual space, right? I mean, for example, you might need to define something like a variable, but as long as the number of the variable you define is not a function of the input, for example, it doesn't really grow with the input size, then using constant number of the space, which is just one. But in certain cases, you might have this one is proportional to the input. For example, in the 2-sum, right? In the 2-sum, we say one of the methods is using hash table. For example, example is like if using hash table, then the space complexity because if you have because the hash table size is roughly proportional to the the number of the input you have, basically the number of the array. That's the reason. But this is something actual, right? This is not on the input you are doing. This is you need to allocate actual memory for the hash table. That's where this one, and so later, when we one of the things we talk about essentially is space complexity and the time complexity. They can trade one for the other. They can trade one for the other. That's also one of the one of the idea about how to improving the running time, because if you, I mean, without any, that's just the reason I say analysis algorithm is not simply as like 1, 2, 3, right? So it's you have to look at the things in several different aspects. For example, both space and the running time. And if you want to optimize the time, you can maybe sacrifice for space. Things like that, right? So yeah, okay. So that's pretty much for this one. Then let's go back to talking about the sliding window problem again. So as I said, sliding window. Let's recap. Sliding window efficient, well, effectively handling adding and deleting at the same time keeping the statistic you're interested in on the sub collection, right? So we kind of like talking about the maximum and the minimum. So although the example we're doing is maximum, but the minimum is really the same, right? So let's think about sliding window, some other stuff, right? So for example, let's do this. Right? So for example, sum, if you're looking at the sum is easy, right? Sum, when you do the update, sum update basically is the new sum is from I plus 1 to I plus k. This can equal to you can just update it based upon previous one, which is I plus k minus 1, then plus, suppose this array A. You want to add in the new element, same time minus the old element, right? So sum update is very easy, right? Product update kind of like similar, but you have to worry about the zero case, right? Because assuming if there's no zero, then this is easy. So you multiply, this guy, then you divide by AI, right? Yeah, something like that, right? So this is essentially that's we kind of talk about the maximum minimum you can use in monotonic stack. What about the median? Median, we're having two different ways we can do this one. One of them is you just keep the full order, right? One of them just to keep the full order. So for this one, it's gonna doing the same thing as as the the maximum. The only difference is in this case, if you know the number of elements in the set, you can find out the median will be the middle one, right? The median will be the middle one, right? So that's like one way. The other way is using two heap. Right? So this is a very interesting idea. So I'm going to show you here. So let's think about this sub collection inside of this one, okay? And let's think about what is the median. So suppose this one is in order, then the median essentially is the middle guy, right? So this is the median, right? Then this is the left element. But what do we know about that one? Essentially, it's the left element should all be less than or equal to the median, right? Similarly, this is the right element. What do we know is the right element should all be greater or equal to median. Okay, what does that also mean is, if you just look at the left-hand side collection, median is the largest one in this left-hand side, right? Right. So by the similar reason, median is the minimum on the right. Okay. So because of that, we will keep two heap. So we will keep one heap here, which is the maximum heap. Then we're going to keep here, which is a minimum heap. Then the next thing we want to do is we want to keep the size stiff. Is less than or equal to 1. Essentially, every time we want the size of these two heaps, they are either equal or they differ by 1. Okay. So this is like, for example, if one of them has more than 1 than the other one, then we can just keep pumping. Because, for example, if the left one has, for example, 2 more than the element than whatever the one in the minimum heap, then on the right, what we can do is we can pop in the element from the left to insert into the right. The reason we can do that is the one in the top of the heap on the left is the maximum in that heap, right? So so by moving this one to the right, it will not changing the kind of like some kind of like ordering, right? Because it is the largest one in the left. Now you put this one into the right. Okay, so yeah, so this is kind of like a very nice trick you can do to keep the median. Of course, there are like some other so I guess right now we only show like the several potential the thing, but if there's any new like a characteristic they being asked you to compute on this subcollection, you can kind of like using some like similar way to analysis, that you find out what's the best one you can use for that particular cases. Okay, so but I would say this is already the most common one, like sum product, maximum, minimum, median, right? So I think this is already the most common one. Yeah, and also overall the idea is when I'm moving by shifting by one position, I don't really want to regenerating everything. I want to somehow reuse whatever previously already have. I want to use whatever the previous already have in such a way like I can minimize the work I need to do. Okay, so this is essentially the one of the fundamental ideas in terms of the algorithm, optimization. Okay, so next one we're gonna talking about something slightly different. So one thing is I realized some of the homework I was given in in the last 1 or 2 weeks is not ideal. Okay, because the problem is some of the homework actually, although it contained the topic we discussed, but it also requires some actual knowledge we haven't really talked about yet. That's the reason, so we might need to revisit some of this homework. Okay, so this is number one. The second one is there is this topic. I think, well, the topic itself is pretty important, but I originally tried to skip this one because I was under the assumption that everybody probably already knows that, but I feel like I probably should not make that assumption. So I better just I would rather let's go over that and do some very, like go over some of the the problems, and because this is so fundamental, so important. Okay, so this is about the customized comparator. Okay, this is about the customized comparator. So we need this one in two different cases. One is sorting, right? The other one is, the heap priority queue. I think some of you probably already know that. So this one itself is not very difficult. I'm just gonna, I will post some of the the resources there. But essentially, is you just need to know. Okay, well, couple of things. Number one is this, right? Number one is in both C++ and Java, we have the primitive type and the object and the class, right? So for the primitive type, you don't need to worry about the comparison because language already provided the default comparison for you, right? So so you don't have to worry about it. But for example in Java, I think okay, this one also slightly differ a little bit from Java and the C++. So in Java, like if you want to implement your own class, if you have your own class and you want object of that particular class can compare, for example, if you want using sorting, or they say there's one, you do need to implement either the comparable or comparator interface. So this is an interface. I will show an example. The example is also very simple. What you need to watch out is this. In your class, you will have several property, right? If you have multiple property, most time you only using one of them as the key comparator, right? So, well, I guess always say use one as the primary comparator. So, but you have to think about, whether this attribute is always unique, right? If they are not unique, essentially is when two objects, they have the same value for this property, was that actually affecting, your algorithm, okay? If you feel like that's the case, if the primary is equal, if the primary property is equal, you need to considering the second property. Okay. I hope you will not. I hope you don't need to, set into this situation. But I do. In some musical problem, you will have this problem. Essentially, is like the primary property is the same. Then, if you did not specify under that condition what's the ordering for these two objects will be. For example, if you just say, okay, let me compare this property, if they are equal, then essentially these two objects will be appear in a random order in the collection. For example, A and B sometimes A may come before B, or A may come after B, but sometimes this will screw up for you in some like edge cases. Okay, so so that's the reason you have when you implement this one, you really need to think about, okay, if I compare this one, awesome, but if these two are, if I have two objects that have same value of this one, you think, does that actually matter, right? You know, maybe it does, or maybe it does not. Okay, so that's, you know, that's number one, right? In C++, I think, because in the use code in C++, most time people don't really implement a class. They don't. They're probably using struct, right? C++ is slightly a different story. Okay. I mean, you can using struct plus the plus two things. One is the either you do operator overloading. For example, you can overloading this you know, less than operator, or you do I think there was something called let me see what they I think you can also provide your own, like you know, you can also provide your own, like, you know, the yeah. So basically, is method one is overloading the less than operator. So this is the one, right? The other one is you can also implement your comparison, you know, function. Okay. So remember, if you do the comparison function, remember the parameter is a better parameter need to parsing by reference. Okay. Basically is you know, this emphasize, you know, don't pass in the object. Okay, don't pass in object. So this is a common, you know, principle in the C++. However, in C++, you know, if you don't want to define your structure, you can also using pair. Pair, for example, there's just like the first and the second, right? So remember, pair, C++, if using pair, it will always comparing the first, then comparing the second. So it will, so this word looks like pretty dumb, but what? So because of that, one of the trick is when you like you know, construct, you know, this pair, you just put the one you want to compare into the first. Then you can directly call the out of box, you know, sorting or the heap one. Okay. So yeah. So this is something that's kind of like very it's, you know, pretty handy in the C++. So we will show some example for this end from this regard. We just okay. So oh, okay. So let me looking at this one. So this is one of the example in the so basically this is one of the example. I mean, this is in last week's homework, essentially for the pair up, right? For the pair up. So for this particular problem, your input contain, like, you know, every row contain two number. One is the output of the count. The second one is, you know, how many cow will have this output, right? So essentially is so you probably gonna create a class called cow, then with two property. One is called count, the other one is called output, right? So then in here you can implement the comparable. You can implement the comparable, the interface, implement this method. Then after that you can call the sorting. Then you can call array.sort. Okay. If you want to call array.sort, because it's sorting an object, so you have to implement this. You have to implement this. Okay. You have to implement this. So this is like in the Java example. Then in the C++ example, sorry, no. So this is wrong one. This is the wrong one. Let me just do DDD. Okay. This is the wrong one. So yeah, the Montooth one. So this is the one I was talking about for the. This is also in the homework. So okay, so this is the one basically say okay. So in here, I'm using the okay. So for example, we reading the edges. Edges has a three property. Basically is the kind of like a source vertex, target vertex, and the weight on the edges. Weight on the edges. Okay, so you have these three property. So I'm using this pair of pair. So because by default it will be comparing this guy. It will be comparing this guy. That's actually the reason when I'm making the pair, I'm making the weight add here. I'm making the weight add here. Okay, I'm making the weight add here. So similarly, in the next one, we have this query. In the query one, we have three values. One of them is the constraint k. The other one is the vertex ID. And at the same time, we need to store the index. So again, because I need to sort it based on the k value, that's the reason I put the k at the first element. Okay, at the first. So then you may ask, okay, what is this? This basically says using the out-of-the-box sorting function, sorting this collection. But in this particular case, because by default it will sorting from small to large. But if I wanted the reverse order, so I just need to pass in, the greater function. The greater function will be reversed order. So I think this is the same as Java as well. By default, it's sorting from small to large. If you need to sort it reversely, in Java there's something called the reverse order, right? Let me just okay, so yeah, there's something called the collection.reverse order. So it will just do that. And also in the customized comparator, you can also implement this one in such, essentially is so basically is this. So okay, so the idea is this. This guy gonna return an integer. Okay, this guy gonna return an integer. So it will return 0 means two objects are the same. From this comparison, it will be the same. It will return -1 if you want that this object is before the one you try to compare. It's if you return something positive, then whatever the one you compare will be before you. That's actually the reason. The simplest way to basically say like a reverse order essentially is you just reverse the result, or in other words, you can say you reverse this. For example, you reverse this to ordering. In here, I'm return this dot output minus cow dot output, right? I can also return because I wanted the output to sort it reversely. I think that's the case, right? Yeah, let me just do this. Yeah, so essentially, if you want to reverse order, you can just previously the easiest way you just multiple -1. Okay, so that way like if you implement your customized comparator, okay, and in this case, if two output are the same, I don't really care. That's the reason I did not implement But other than that, if you can think about, okay, if they are equal, then you can compare the other property, which is the count. Okay, so this is about the customized comparator. Okay, so this is for this one. Okay. Okay, so next one, we're gonna talking a little bit about the homework. Okay, so okay, two things. One is I will be running a little bit over time. So, but if you have something you need to leave, you can leave, and you can watch the video later. That's number one. Yeah, I apologize for that, but I do want to go over some of the homework. So and also the one I'm gonna go over today is the week 3 homework, which is still on the graph and the DSU stuff, and we will go over a little bit more. We will go over the week 4 and basically the 2-pointer homework like next week. Okay, so that's basically is the plan. So let's look at this first question. Is this one is the wormhole sort. So this one, unfortunately, is this one has 2 pieces. This one has 2 pieces. There's one piece we did not really talk about, which is the binary search part. But so that's reason we will need to revisit this problem again. But so basically the whole idea is this, right? The whole idea is like well, couple of things here. Number one is this. Number one is how do we determine? Well, number one is how do we determine whether because initially this one is in not in order, right? So for example, in here, I think 2 and 4 are in the order, 1 and 3 are not, right? How do I know? Eventually, after the wormhole, I can sort it. I can rearrange 1 to the first position, 3 to the third position, right? What does that really mean? What does that really mean? From graph perspective, what does that really mean is these 2 nodes are connected. These 2 nodes must be connected. Essentially, is from the DSU perspective, basically means they must belong to the same connected component. They must belong to the same connected component. So this is one of the key insights for this particular problem. Then the second one is basically on top of that, essentially say, okay, because they want to find out the optimal, like the width for the wormhole, that part was require, the binary search. Okay, so for today, let's look at the, say suppose you're given. Let me maybe show the. This is for the wormhole. Yeah, this is 2020. By the way, I will post this one after this. Okay. Oh, can you guys see the screen here? Yeah, let me see this. Oh yeah, yeah. I think you can, right? Okay. Just want to make sure everybody can do this. Okay. So, okay. So here, okay. This is a list of the position. Essentially, is kind of like the vertex, right? This is the wormhole list. Essentially, in this case, essentially is the edge list, right? Then we reading this input was n vertex, m edges, right? Then I'm initialize this one. Then I'm reading the edges. So reading the starting end and the weight. Then I'm putting this one into the wormhole. Basically to put into the edge list. Okay. So this is the binary search part. We can currently ignore that. So, but you can imagine in here, once you get a given, the middle basically will be a given like width for the wormhole. Okay, then we need to check whether this is will allow us to sort it properly. Okay, so in the is valid function, this is the key for the DSU for the the. So if you think about this one is very similar like the number of the island, very similar like the number of island, right? That's like the reason we are doing this one also kind of like the number of the island. So we initially initialize this roots, the roots vector, which is the same as the number of the node. Then we run run the DFS for the number of island, right? So the only thing that's actually is so if you look at the DFS, so DFS essentially say, okay, I have some like index. So essentially, if two vertex they can be connected by the wormhole, they will be assigning as the same index, right? Just like in the number of island, if you want to count the number of island, you can say, okay, I go to the first island, then I mark all the cell for this island as 1, right? Then I go to second island, I can mark all the cell belong to this island as 2. This is essentially the same idea, okay? Same idea. So then I go to the first island, I go to the first connected component, I will marking everything as 1. After that, I'm incrementing my counter, so then the next component will be assigned a value of 2. So in this way, if you belong to 2 separate components, you will not be getting assigning the same like rooted index. Okay, so then the caveat in here is this: supposedly your wormhole list basically give you the edge list, right? But in this case, we have this extra caveat essentially say, okay, you can only go there under these 2 conditions. One is, this weight is larger than the given constraint, right? Is a given constraint. This is number 1. The second one is you have not been visited, because if you already visited, then your rooted value should be something larger than 0. Because initially this rooted vector, everything is assigned as 0, right? If you are visited, you will assign something larger than 0, right? So this is essentially the key. So after this one done, then we will basically find out all the connected components. Then this is basically the one to check whether I can properly sort the the array. The key is basically is the element at the position I and the position I, they must belong to the same connected component. Just remember, essentially is like, 1 is initially at the 3, right? In order for 1 to go back to 3, essentially is whatever stay in the 1 must be, whatever stay, in the current position 1, they must belong to the same connected component with, the 1. Okay? If they do not belong to the same, basically, if the root are the same, then they belong to the same connected component. If they are not, then you cannot, then there's no way for you to sort it back. For example, if 1 is not connected to that, then you have no way to put 1 back to the position 1. So that's basically is the key. That's basically is the key for this particular problem. Okay. So this, yeah. So you will find out like we are currently learning like each like some kind of like a subtask kind of thing. For example, DSU, this is a connected component is one of the, and in the actual context, they really like to mix this 2 or 3 different problems together. So basically, when you're solving this one, you will find, oh, I can decompose this problem into 2 or 3. So this is the example. Basically, is decomposed into binary search plus the connected component. All right. So yeah. So this is for this one. Okay. So let's see. So this is the first one. Then the second one I want to show you is this guy called the Moontube. Moontube, although this one is in gold, but this one is has two very important idea. Has two very important idea. Okay, so okay, so this part is relatively well. So this part essentially is you have essentially donating the edges, right? Donating the edges. Then and also their relevance, right? The one key inside, well, we will show two things here. Number one is this. This is the query. This is a query. This is a query. So one brute force way, or essentially say, for each query, I can run the DSU. I can run the DSU. Then I will find out how many video, essentially is from this given video, from their like edge relevance relation, how many recommended video I can generate. This essentially is also the connected component problem, right? Connected component problem. So we know how to do that. So I guess if this one has a civil version, then probably you can just say, okay, for each query, I'm running a DSU. Okay, for each query, I'm running a DSU. The DSU really just doesn't have to do the you can also do the the DFS one, right? You can do the DFS one, Okay, so but if you do this for the gold version, you will fail. It's not because you generating the wrong answer, because every query you have to rerun the DSU, right? So that's the problem. So so the trick for this one is I have this query, which is something what we call offline query. Essentially say, before I run my program, I already know what kind of query I need to run. Okay, this is unlike the online query. Online query essentially is the query just to keep coming in. You don't know which one they're gonna come. So so you cannot pre-calculate the results. You cannot pre-calculate the results. So for this one, one of the key idea is I have offline query. I do not necessarily run the query in this order. I do not necessarily run this query in this order. Okay, so I can run this one in an order in such that I can do the incremental build-up. I can do the incremental build-up. So the key here is this. So I get the list of the query. I sorted their k value from largest to smallest. Okay, because this one is similar to there's a problem we did for the Mooncast, right? The Mooncast essentially is two video. They will only be recommended if the relevance is larger than the given k. Is larger than the given k. Okay, it's larger than the given k. So basically means, for example, initially I can run when k equal to 4. Then basically is then all the edges with the relevance larger than 4 will be considered as connected. If you have relevance less than 4, you will not. You kind of consider they are not connected. Okay, but if I'm running now after I run the one with 4, if now I run the one with 3, the good news is I do not need to rerun the part which is already get run, because if some relevance is larger than 4, it will automatically larger than 3. So which means I can build up my graph on top of the previous results by adding the relevance is less than 4 larger or equal to 3. Okay. So I'm just keep adding the edges. I will keep adding the edges. But I think I need to this one. This is a very, very important. Okay. So this is called the Moon tube. So inside one is incremental buildup. Okay, so for example, I'm sorting both the k value and the edge relevance value, right? This is in the let me see. Yeah. So you can think about, suppose this is what the K1. So this is this is all the relevance value larger than K1. So I was using this edges to build the graph. Then when I'm doing the K2, when I'm doing the oh my god. When I'm doing the K2, I can just build upon on that by adding something like K2. So this will be containing all of this one, right? So this is right. So K3, right? So you see when I do K3, because if they greater than K1, they're gonna greater than K3. If they greater than K2, they're gonna greater than K3, right? So when I do K3, I only need to worry about the incremental part. So this is the key, incremental. This is the key, okay? This is the key for this one. Then you don't have to redo the work, okay? So let's look at the code. Dun, 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 dun. So this is the number one. There was another one. Let me just show you. There's another very important insight. They basically they did this like they did this kind of like the okay. So let's first show you the okay. So in here, okay. So I'm reading the N and the Q. So this is reading this is storing the edges. This is storing the query, right? Storing the query, storing the edges. They sort both edge and the query. Sorted the edges are in a reverse order based on the weight, okay? Sorting the query in a reverse order based on the k value, okay? Okay, so I'm doing my DSU. I will, okay, so in here the DSU, I will expand a little bit more on the DSU. So the DSU in here is a little bit different. So okay, so in here I'm having my result. So you see here, I'm processing the query. Now remember, query is from largest the k value to the smallest k value. I'm having an index to go through the edge list. Initially, this is starting from 0, so I'm putting the current k value. Then, so I will keep adding the. Basically, is whenever you so if this one is less than the size, that's the common one, right? Then also this edges, the k value is larger than the current k value, which means this edges can be activated. Okay, this edges can be activated. Then I'm adding the edges to the DSU. Adding the edge to a DSU essentially is you just unite basically to the uniting these two vertices, right? Uniting these two vertices. So this is uniting these two vertices. Then I'm moving my I'm moving my index by 1. So remember, when will this one stop? This one will stop either it's you have no more edges, or it will stop at the first edges, which is have the k value which is smaller than the current k value. Right? What does that mean? That will be exactly the next one. That will be exactly the next one you can processing for the next smaller k. Okay, for next smaller. That's the reason this whole edge list will only be running through once. Only be running through once. Okay, only running through once. Okay. So this is essentially the trick. This is essentially the incremental build up. That's actually the reason you just keep adding the edges on this DSU structure. You also the whole DSU only be built once. Only be built once. You can kind of like think about this build in several stages, but it's still incremental build. It's never you never rebuild the whole DSU. You only build DSU once. Okay. So this is basically the incremental the build up one. Okay. So in terms of this DSU, okay, remember the problem here is the question here is asking, say, okay, after I run that query, the query asking, say, oh, how many video will be recommended to me? What does that mean? That basically means for the same component, for same connected component, including this query, the video, how many, essentially is considering the connected component, including this current video, how many other video are also in the same connected component? What does that mean is we need to very fastly to compute the size of the connected component. Okay, the size of the connected component. So this one was using, okay, so let me just let's just using this one whiteboard to understand. So okay, so if let's recall, the standard one, you having this like integer array. Initially, the roots value is assigned to the index. Essentially, say okay, every okay, a standard one. No, what I just did. No. right? So I is root if root I is equal to I, right? So this is the standard one, right? So in here, we do things slightly different because, well, I guess if you're using the standard one, what you need essentially is you will need two array. One of them is just following the standard one. The other one is you can using the other array with the same size to store the size of the current component, right? The size of so we did a little bit of modification, you know. So we basically say roots I will basically so first is this I is roots. Okay. Remember, we don't using the positive integer because positive integer essentially will be contributed into the index. So it's I is root if root I is less than 0, and also if I is root, and also the root I will equal to the negative size of the component I. Okay, then if I is not a root, then root I will still be the same. We'll basically store the parent, the index or the parent. So this is kind of like you combine two information into the same array. You combine two information into the same array. Okay, so let's try to see this. Okay, so let's see the code. Okay, so here, right? Okay, we initialize this vector. This is easy. See here, okay. Initially, I initialize everything to be -1. Why? Because initially everyone is on its own. Everyone on their own. And also every component only have a size of 1, and they are negative. Okay. So let's see this one. This is easy, right? Same set. Get will always give you the roots index. Get will always give you the roots index. Okay. Get will always give you the roots index. If they belong to same roots, then they are connected, right? Okay. So in here so one of the ideas in here get. Okay. Get. When do we reach the roots? If this value is negative, then we know it's a root. Other than so basically this kind of like a recursive code said, oh, if this one is not a root, I just get the parent, right? Get the parents, right? So whenever you call get, it's if it's not a root, it's basically going up at one level. Okay. Then also in here, as we say, if basically get x will get you the roots index of x, then the value is the size for this component, but it's negative. So if you do negative of that one, you get it. Okay. So these are all. So then the whole trick is happening in the united here. You united, find the two roots. If roots are the same, do nothing. If roots are the same, do nothing. Okay. So this one basically say, okay, now both are the roots, right? So compare these two values. Remember, if both are roots, these two values, they're all negative. Then if EX is larger than EY, basically means, I don't think this one is this step is really necessary, but this is kind of like try to make them in a canonical order. Essentially say, if EX is larger than EY, remember they are both negative, which means the absolute value of EX is actually less than EY, which means X is the roots for a smaller component, Y is the roots of the larger component. I guess this one tends to always merge the smaller component into the larger component. That's the reason they do the swap. They do the swap. Okay. Now what we do is okay. So we basically merge the size, because both numbers are negative, adding together, right? So for example, if you -1 plus -1, you get -2. That's essentially you merge two nodes, right? So you merge two nodes. Basically, you merge the size. Then let the smaller one point to the, because X is not, X will never be negative. Then now EY point to X. EY point to X. Basically is Y is no longer a root. Y is no longer a root. So by doing this one, you united the two elements, or you not united the two components. Okay. So other than that, I think that the rest is relatively easy. So basically, is I'm just keep doing, I'm just keep doing that. Okay. So yeah, I do think that this problem has some very like useful and insightful the things we can learn. For example, one of it is this: how do you well, number one is definitely incremental build up. Incremental build up is probably the number one way you can optimize your algorithm. Okay. The second one essentially is how do I combine? Essentially, I have two pieces of information. How do I combine them in the DSU case? Right. One is whether this one is the roots. The other one is the size for the connected component. Okay. Okay. Sorry for the delay, and I will post the homework very soon. And do you guys have any questions so far? Okay. If no, I guess as always, if you have any questions, feel free to message me, or you can just post in the the channel. And other than that, I guess I will see you next week. Okay. Bye.